In this video, we will explore exponential functions and logarithmic functions. To differentiate linear growth and exponential growth, linear functions grow at a constant rate, meaning they add or subtract the same value repeatedly, while exponential functions grow at a constant percentage, meaning they multiply the same ratio repeatedly. Graphically, a linear function forms a straight line, while an exponential function curves upward, means it grows exponentially, or downward, means it is an exponential decay. An example, suppose given a linear function f of x equal to 2x plus 1, and when x is from 0 up to 3, the outputs are 1, 3, 5, and 7. And you can see here that from 1, it adds 2 in each item. While an exponential function, f of x equal to 2 times 3 to the power x, when x is from 0, 1, 2, and 3, the outputs are 2, 6, 18, and 54. So you can observe that in each item, it multiplies 3 times, causing much faster growth than a linear function. For example, determine whether the quantity described is changing in a linear function or an exponential function. For the first part, Emily invests 1,000 in a savings account that offers 5% interest per year. So here, this is an exponential function because there's a growth in 1,000 by a percentage or 5% interest per year. For the second part, a factory produces 500 cars every month, and this is a linear function because there is an increase by a fixed amount of 500, which is 500 cars per month. For the third part, a computer's processing speed doubles every 18 months due to technological advancement. This is an exponential function because there is a multiplicative growth, which is doubles every 18 months. And for the last part, which is an exponential function, a company revenue grows by 8% annually due to expanding market reach because there's a growth in percentage, which is 8% annually. Let us define exponential function and logarithmic function. An exponential function is a function of this form, where a is a positive number, or a is greater than 0 but not equal to 1. C is not 0, and x is a real number. Let us analyze these conditions. For c, when c is 0, 0 times e to the x is equal to 0, so the function is not exponential. The function will be a zero function. For a, when a is 1, 1 power x is always 1 multiplied by c is equal to c, so the function becomes a constant function. And when a is negative, having a negative base, and the power is a fraction, like square root of a negative number, it will be undefined. The base a is a growth factor, and c is the initial value. We get the initial value by putting 0 in x, so f of x is equal to c. So that is why c is called the initial value. And in logarithmic function, to the base a, this is denoted by y equal to log base a of x, if and only if x is equal to a. So this is how you will write the logarithmic function to exponential form, and from exponential form to a logarithmic form. So the condition for a is the same as exponential. A must be a positive number, but not equal to 1. And you can read this as y is the logarithm to the base a of x, or log of x to the base a. Regarding the domain of an exponential function is a set of all real numbers, but the domain of logarithmic function is always positive numbers, or greater than 0. Let us try to express exponential form to logarithmic form and logarithmic form to exponential. Suppose, for example, we have a 2 cubed equal to 8. We can write this exponential to logarithm as log base 2 of 8 equal to 3. So to see the relationship, they still have the same basis. The base of exponential here is 2, and the base of this log is 2. And then the power in exponential becomes the answer in log, and the answer in exponential is the function in log. There are two types of logarithmic function. The first one is the common logarithm. The function y equal to log base 10 of x is commonly written as log x. So this is a logarithm with base 10. Another one is natural logarithmic function, which is y equal to log base e of x, or it can be written as y equal to ln x. For this example 1, change each exponential to its equivalent logarithmic statement and vice versa. For the first question, 3 is equal to square root of 9, and we're going to change this to logarithmic form. So first, let us change square root of 9 in rational exponents, and that is 9 raised to 1 half is equal to 3. Then changing to logarithmic form, so we will have log base 9 of 3 is equal to 1 half. So see the relationship between them. So this is the base, this power is the answer for this log, and this 3 is the function in this log. For letter B, the given is log base 3 of 1 over 9 is equal to negative 2. So we're changing this to exponential form. So let's start with the base of this log, which is 3. So 3 to the power negative 2 is equal to 1 over 9. Then see again the relationship between them. This base is the same base here. The negative 2 here is the power, and 1 over 9 is the answer for this exponential. Next question is log x equal to 3. So we're going to change this to exponential form. So let us start changing this log x with base, which is equal to 10. So log base 10 of x is equal to 3. Then we can now change to exponential form, starting with the base 10, then power 3 is equal to x. Then check the relationship. So our answer is x is equal to 10 cubed or 1000. Next question is e cubed equal to x plus 1. So we're going to change this to logarithmic form. So first, take the log of x plus 1 with the base e is equal to 3. Now check the relationship. Then log base e is a natural logarithm which is usually written as ln or ln. So we're changing this to ln of x plus 1 is equal to 3. The next example is negative log base 2 of x minus 1 is equal to 3. So we're going to change this to exponential form. First, you will notice that this log is multiplied with negative. So first, we have to isolate the log on one side. So what we're going to do is to multiply both sides by negative 1 to make it positive log. So we will get log base 2 of x minus 1 is equal to negative 3. Then, changing this to exponential form, start with the base 2, and then the power is negative 3 is equal to x minus 1. Then check the relationship. Then for the next question, 1 minus 2 power x is equal to negative 4. So we're changing this to logarithmic form. So again, you can see that this exponential 2 power x is multiplied with negative. So again, we should isolate 2 to the power x on one side by moving negative 2 to the power x on the other side and negative 4 on the left side. And then, so we will get 2 to the power x is equal to 1 plus 4, or 2 to the power x is equal to 5. So now we are ready to change to log form. So getting the log of 5 with the base 2 is equal to x. Then check the relationship. In example 2, we're finding the domain with logarithmic function. So for the first example, f of x is equal to log base 5 of 1 plus x over 1 minus x. Let us recall that if the given function is log x base a, its domain is x greater than 0, so it cannot be a negative number. So since in this given function it is a log function only, then we will apply the rule in finding the domain of log, which is this expression must be greater than 0. And we're going to solve for x here. Since this is a rational inequality, so solving x in a rational inequality, we have to make use the sign analysis. So in sign analysis, we need the zeros of the numerator and denominator. And they are negative 1, because the 0 here is negative 1, and the 0 here is positive 1. So we will have negative 1 and 1 in the real number line. And both of them open because this is only greater than 0. Then we will get the sign on this inequality on the right side by choosing a number after 1 or from 1 to infinity. So let's say 2. If we will place 2 in this given fraction, the answer is negative 3, meaning the sign here in this interval is negative or less than 0. So we will put a negative sign. And then on this interval, you can select another number, let's say 0, and put in the given. And then on this negative 1 to minus infinity, you will select a number which is negative 2, and you will place again on this fraction and then get the sign. But here, what I'm going to do is, since this 1 plus x, the power is 1, and in this 1 minus x, the power is also 1, meaning both of them multiplicity add. So meaning, from this negative, it will change the sign on this left side. It will be positive and then negative. So now, since this fraction should be greater than 0, meaning we need a positive sign, so we are selecting this middle interval, which is negative 1 to 1. So the domain of the given function f is interval negative 1 up to 1, where negative 1 and 1 are not included. For the second example, the given function is log of x plus 4 divided by square root of x minus 3. So here, the given function is not only log, the given function is a fraction, meaning we will apply the rule in finding the domain of a fraction or domain of f over g. So let us start with the domain of f, or the domain of the numerator. Since the numerator is a log function, so we know that in log function, this x plus 4 must be greater than 0. So solving for x is greater than negative 4. And then on the denominator, since there's a square root, and we know under the roots, this x minus 3 must be greater than or equal to 0. But since this square root is in the denominator, meaning we have to remove the 0. So it means we will set the x minus 3 to be greater than 0. Or solving for x is greater than 3. Then finding the intersection of these two, so let us graph or plot negative 4 and 3 in the real number line. And then if we choose x greater than negative 4, meaning we will shade from negative 4 on the right side. And then x greater than 3, we will shade from 3 to the right side. Then getting intersection of these two, so we will have the domain which is from 3 to infinity. So that is the domain of the function f. Next is the graph of exponential and logarithmic function. So let us start with exponential function f of x equal to a power x. So the condition for this base a is that a must be positive but not equal to 1. So it divides in two intervals or two types of graphs of exponential. The first one is a is less than 1 but greater than 0, and another one is a is greater than 1. So let's take a look when a is less than 1. When a is less than 1, the graph of the exponential a power x will be a decreasing function like this. And when a is greater than 1, the graph of the exponential function a power x is an increasing function like that. Now let us explore the graph of logarithmic function y equal to log base a of x. So as we know, the graph of logarithmic and exponential functions are symmetric with respect to y equal to x. So this blue is the graph of exponential, and its inverse, which is logarithmic, is this pink. And the other one, this blue is the graph of exponential, and this pink is the graph of its inverse, which is logarithmic function. So similar with the exponential function, a must be positive but not equal to 1, and it divides into two types of graph. One is a is less than 1, the other one is a is greater than 1. So when the graph is a less than 1, same as exponential function, the graph of logarithmic is a decreasing function. And when a, or the base, is greater than 1, the graph of logarithmic is the same as exponential, which is an increasing function. In finding for the asymptote and range of exponential and logarithmic functions, there can be available formulas for this. So for this example 1, we can complete the table by finding the asymptotes and range of the following functions using this formula. So for the asymptote, let us start by finding the asymptote of logarithmic function, which is the first function and the third function. As we know, the asymptotes of logarithmic function are vertical asymptotes. And the equation for vertical asymptote is x equal to, so you will base from this by equating x minus 2 to 0, so x is equal to 2. And then for the third function, which is ln of x plus 1 minus 4, the vertical asymptote is equating this x plus 1 to 0, so you will get x equal to minus 1. And then for the horizontal asymptote of exponential function, which is the second function, so horizontal asymptote, the equation is y equal to, you will base on this vertical shift, so y equal to 2. And for the last equation, or the last exponential function, so the horizontal asymptote is y equal to positive 3. So for the range, let us recall that the range of logarithmic is equal to the domain of the exponential. And we know that the domain of exponential is always all real numbers. So we can start finding the range of logarithm, which is the first function and the third function. So we are writing that the range is from minus infinity to infinity, and the range for the third function, which is ln of x plus 1 minus 4, is also minus infinity to infinity. And then for the range of the exponential function, usually this is the um, hardest part to memorize or to remember, because this is the formula for the range. But let me give you a technique on how to find the range of exponential easily. So you will start on checking the sign of this exponential. This e to the x plus 4 is a positive, meaning the range is up to positive infinity. And the left side is the constant number here, which is the vertical shift, which is 2. So the range here is 2 to infinity. Then for the last exponential, so we can see that the exponential here is e to the x plus 4 is multiplied with negative, meaning the range is up to minus infinity on the left, and the right side is the vertical shift here, which is positive 3. So the range for this exponential is negative infinity up to 3. In this example 3, we will determine the properties of logarithmic function and analyze its graph. So first, we will find the domain of this function. Since the function is a log, we know that x plus 4 must be positive or greater than 0. And then solving for x, so x is greater than negative 4. So we can leave this answer for the domain of f. Or if in the given, we have to write in interval notation, so we can write from negative 4 to infinity where negative 4 is included. Then for the range, since the function is logarithmic function, we can relate the range of log as the domain of exponential. Since we know that the domain of exponential is all real numbers, so it means the range of this log function is equal to all real numbers. Next is the asymptote. The asymptote of log function is vertical asymptote. And the equation for vertical asymptote is x equal to, we have to base this vertical asymptote in this x plus 4 by equating x plus 4 to 0. So vertical asymptote is x plus 4 equal to 0 or x equal to negative 4. So this is the equation of the asymptote of this log function. Next is finding the intercepts of the function f. To find for the x-intercept, we will set y or f of x to 0. So we will have an equation 1 plus log base 2 of x plus 4 equal to 0. And then to solve for x, we will have to get rid of this log. So we have to prepare this changing to exponential form. And to do that, we need to isolate this log by moving 1 on the other side. So we will get log base 2 of x plus 4 equal to minus 1. Then we are now ready to change this log to exponential form. So we will get 2 to the minus 1 is equal to x plus 4. So from this, we can now solve for x by moving 4 on the other side. So x will be equal to 2 to the negative 1 is equal to 1 half. Then moving 4 on the left side, we have 1 half minus 4, which is equal to negative 7 halves. Negative 7 halves or negative 3.5. So I just changed this to decimal because we need to plot this x-intercept later. Then for the y-intercept, we set x equal to 0. So you would just substitute 0 in the given function in x. So we have y equal to 1 plus log base 2 of 0 plus 4, which is equal to 3. So 3 is the y-intercept. So to continue on this example, let's get now the inverse of this given function. So we will follow four-step rule in finding the inverse of the function. So for step 1, we have to replace f of x by y. So this function will be y equal to 1 plus log base 2 of x plus 4. The next step is to interchange the x and y by replacing x by y and y by x. So from this equation, we have y will be x and x will be y. And then for step 3, we have to solve for y. And to solve for y, we have to get rid of this log again. So we have to prepare this equation to change to exponential form. And to do that, we need to isolate this log base 2 of y plus 4. So we're going to move 1 on the left side. So the equation will give us log base 2 of y plus 4 equal to x minus 1. So now, since this log is already positive and isolated, so we can now change this to exponential form. So start with the base 2. The base 2 is base 2 to the x minus 1 is equal to y plus 4. So we can now solve the y here by moving 4 on the other side. So y is equal to 2 to the x minus 1 minus 4. Then, for the last step, change y or replace y by f inverse notation. So f inverse of x is equal to 2 to the x minus 1 minus 4. So this is the inverse function of the function f. Then for letter f, we will find the domain of the f inverse. And in finding the domain of f inverse, so we have to base from this. So basing from this, since this is exponential, and as we know, the domain of exponential function is all real numbers. And then for the range of the f inverse, since we don't have graph yet, so we can relate the range of f inverse as the domain of the function. And this is where we get the domain of the function. This x plus 4 must be greater than 0, and that is negative 4 to infinity. Then for the last step, so we have to sketch the graph of the function f and f inverse. So let's start graphing the function f. In graphing for the function f, based from the information that we saw from a, b, c, and d, so we have the vertical asymptote of logarithmic function is x equal to -4. So we're graphing it as vertical line and it's broken line. And then after that is the x-intercept, which is -3.5 or -7/2. And then the y-intercept is 3. And then we will have an extra point because we need minimum of 3 points to graph this exponential or logarithmic function. So the extra point here is we assign any number here between -1 or -2 or -3. So I choose -2. So you have to put here in the given function. So when you replace -2 in x here, then you will find y, which is equal to 2. So -2, 2. And now we are connecting these 3 points using a smooth curve asymptotic to this vertical line. So that's the graph of the function f. And now, to sketch the graph of the f inverse, as we know, f inverse is symmetric with respect to y equal to x. So meaning we have to reflect this graph along this line. Or what we can do is, we can get the inverse of this vertical asymptote, which is horizontal asymptote. If the vertical asymptote of the given function is x equal to -4, so its inverse is y equal to -4, and its graph is horizontal line. Okay? And then for these 3 points, what we're going to do here is we have to interchange the x and y coordinates. So if I will start with this x-intercept -3.50, so if we will interchange, it will be 0, -3.5. So it will now be y-intercept, which is this. And then the y-intercept, which is 0, 3, if we will interchange, it will be 3, 0. So the 3, 0 will be the x-intercept. So from the y-intercept becomes x-intercept. And then for this extra point, which is -2, 2, so we interchange this. So 2 minus 2. So now we already have minimum of 3 points. So we can now graph this by connecting these 3 points and asymptotic to this horizontal line. So this is the graph of f inverse.